Hello, everyone. Connection Wednesdays are back after the summer break. We hope you had some really nice and relaxing holidays. It's good to be back. It's good to meet you all of you again. It makes us also very happy to see so many registrations for this first webinar. I think we have an all-time record for Connection Wednesday with over 330 registrations, which is great. And this certainly gives us the motive to continue doing it. My name is Theodore, and both me and my colleague Kostis, who is going to do the presentation, I would like to thank all of you for joining and giving us the opportunity to demonstrate how STatiCa has managed to revolutionize the way that we design steel connections. Before we start, as always, I just wanted to mention a couple of things about the software GoToWebinar that we're using. So if any of you hasn't used this before, on the right side, you see a control panel where you can, of course, minimize it. And you can use this if you want to ask any questions during the webinar. So feel free to write any question you have. I will be following the questions as Kostis will be doing the presentation. I will try to answer some of them, and I think we might have some time in the end to do a quick Q&A as well. So this time, we decided to do the Connection Wednesday webinar a bit different than the previous ones, where we were actually focusing on a customer project and a help desk highlight. And this time we're going to focus entirely on some of the common mistakes that a rookie can make when designing and code check steel connections with StatiCa. So when we have a new user, it's obviously he doesn't have a lot of experience and he might do some mistakes. So we will discuss how to correct these mistakes and how to work faster and more accurately, but also about calculation principles and methods behind StatiCa. So some really important basic knowledge about the software. So whether you are a rookie or not, whether you are a user or not, I hope that there is something for you to learn today. My colleague Kostis has chosen a support request that we had recently from a trial user who has sent us a model to our help desk. As you can see this in the slide, because basically he could not run the analysis. So he sent us a request. He said, yes, this connection, I cannot run it, so can you please have a look? Obviously, we support all the trial users during the trial period. So if any of you are using the trial right now, again, feel free to send us any question you have. So more than this, he was not able to model properly the connection. So he could model up to a point, but he didn't know how to model the top column connection using a lap splice. As you can see in the drawing, the top one is a lap splice, but in the model that he sent us, he was using an end plate splice. So we will have a look exactly how we can change that. So when we actually received this model, we saw certain problems, and we are going to focus on these problems today. So first of all, the analysis was not running, and as you can see, we were getting a singularity error, and we will first of all see why this is happening. Then another problem is that the elements some of the elements have been defined as members and not as stubs, and this is one of the common mistakes that the first-time users are doing. So we will see how we can deal with this. Another problem is that we saw some really big eccentricities in the model. So some members have been defined with a very big eccentricity, and that is something that can cause problems in the analysis. Another problem is that the standard base plate operation that we have would not work for this joint because it included a stub. So we will see exactly how we can deal with that as well. Another problem, as I mentioned in the beginning, is that it wasn't using the lap splice connection. So we will see exactly how we can switch to that. And finally, we examined what we call the fictional node principle. So this is a basic principle in our software, and it is really important that the model respects this fictional node principle. So at the end, we will discuss exactly how we can check this principle, if it is respected or not. So with this, I would like to switch over to Kostis, who is going to start with the presentation. Oh, I think we.
Okay,
yeah.
so hello everyone.
Okay.
Thank you, Theodore. Could you please verify that you can hear me and you can see my screen?
Yeah, everything is fine. Please.
Okay, so we will jump straight to the model that the user provided to us. Now, this is a seemingly fine model, but if I press the calculate button, after the software starts working for a while, we can see this singularity message here. Now, many users do not know how to deal with this situation. So we have created a tool which is really easy to use. And this is the tool that we also use in the software. So when you see singularity like this, you can go straight to the check here. And if I press the check tab, the software, I have to go to strain check because this is an already solved model. If you face a singularity for the first time, you don't need to do this. Okay, I have to pick the strain check and the deformed shape. Let's reduce this value a little bit. And the software displays the unconnected parts. So here we can clearly see that some part of the model is unconnected. The software also displays a table here and gives us a clear message about the position of the singularity. So we know that we have to look on member M3. Let me also zoom in a little bit. And I will also look from the bottom. And we have a first indication that something is wrong because we can see this part of the model here. Since this is my reference model, I will jump back to the original one provided by the user. And here I will try to fix the model starting from member M3. So let's select member M3 to investigate the problem. We can see that the member is highlighted, so we know its position. And the first thing we notice is that we have a really high eccentricity value here. It's 700 mils. Now, we have eccentricities for some reason. You can use them wisely, as we will discuss later on. But in this particular case, where we have a stub operation, this is an indication of wrong modeling. So to investigate, I will change this value to 0. And I see that along with my member, my stub moves. Another issue that is revealed is that we also have member M5 here, which is actually not required, as we will discuss later on. Okay, so let's go to stub 1, and you will notice here that there is a property called X position. This property is set to 0. Now let me change this value back to 700 mils, and you can see that the connection moves along with member M3. The software also creates a stub, so you don't need to do anything to model the stub, which means that member M5 is not required. So we'll uncheck this. When I uncheck a member that is required, the software notifies me about the operations that are depending on this member. So I know that the cut operation, I must deactivate the cut operation. We also see that the software messes up the base plate, so we'll also deactivate this since this is a distraction for us. Okay, let me delete this member. And again, we can see that the same problem exists on member M4. Again, I will click on member M4, and I can see that there is an offset value of 550 mils. Now, let's investigate this a little deeper. I will also activate my wireframe model here. This is member M4. Member M2 is also not required, so we'll also deactivate and delete member M2. And then I will go to the load effects, select one load, and select member M4. We can see its moment diagram for load case LE2. Now, its moment diagram does not extend up to the fictional node. And this is really important. I will show you why, because if I select member M4, we can see that the user has defined these forces in the node. But due to this eccentricity here, the forces are defined on this position here. Now, let's fix this to match the intention of the user. So I will zero out this eccentricity. I will move to the stub, and I will set its X position value to 550 mils. We can see the distance here. Now let me go again, select load case LE2, and this time we can see that the diagram extends up to the fictional node. Another thing that is important to understand is that this influences the applied moments at the member end. And this time we have higher moments than the previous definition, which would probably lead to a conservative result. So let's move back to the solid view. Let me rotate this a little bit. And the next step is to replicate the base plate operation on our stub. So I will copy this operation, and I need to relate this operation to my stub 1 member. But here, if I go to the combo box that contains the members, I don't see stub 1. There is a workaround for this. but I will take the opportunity to demonstrate what we call general anchoring. So let's go and create a new stiffening plate that I will name as base plate. Let me look from the top to define its geometry and switch the view to transparent. I will then set its thickness. I will set its geometry. And last, I will look from the side and activate the wireframe. The user wanted this node to be defined up here. So to fix this, I will lower my plate a little bit, and so we fix this. The next step is to define anchors. Now, to define anchors, defining anchors is the heart of our so-called general anchoring. To define them, I will use a stock bolt grid operation, but instead of using bolts here, I will set this to anchors. The anchors are anchoring a single base plate, so I have one item, which is the base plate. And now I have also to define my foundation block. My foundation block will be related again to the base plate, and we can see now that this is positioned below my base plate. And then I have to set the parameters to match the initial base plate. Let's define the foundation block geometry. We will not stick to the details. Here I'm defining the original shear lag, which was rotated. And I'm also setting the throat thickness of the welds. The next step is to define the anchors, and the anchors are defined in the fasteners category. I will look from the top and switch to the transparent view. I will set my anchors to M36. I will define the row position, the anchor rows position. And then I will also define the columns. And now that my anchors are in place, I will define the anchoring length, their type, and my base plate is ready. We only need to weld our stub on the base plate, and for this I will use a cut-off plate operation. I will apply this on stub 1 related to my base plate. Let's again set the weld throat thickness values. And last, I have to weld the second stub to stub 1, again using a cut-off plate operation. We need to use the surface cutting method since this is a hollow section. And right now, we have a connection that solves just fine. Now, until this solves, Let me jump to my PowerPoint slides because I want to discuss an issue with the lap splice variation that we want to create later on. Theodore mentioned that we have to discuss some basic principles in IDEA STATICA. And this is the fictional node principle. So in IDEA STATICA, there is one basic assumption that the connection must feature a single identifiable node where all members converge, no matter how complex this connection can be. This is true for our connection, but you have to understand that all loads are defined and extrapolated in relation to this node. So when connection components are defined at a distance from the fictional node, and we mean the lap splice, care should be taken and engineering judgment should be applied, as the applied loads at the member end are a function of this distance, like I demonstrated in member stub 2. When this distance becomes too long, then the user should really consider splitting this connection into two separate ones. For our case, we will assume that this distance is all right, and we will go and model it. Now, another issue that we have to discuss is the modeling of this stub. Now, the stub operation does not support lap splices. It only supports end plate splices, like in the picture you see at the right. Now, in order to achieve the result that the user wanted, we need to use a stiffening member for the definition of the stub. And the reason is that stiffening members are different from normal members. They are both defined in terms of rotations and translations around the fictional node, but for normal members, the edge farther from the node should be either supported or loaded, and this is not the case for stiffening members. Also, normal members can be classified using stiffness analysis, while stiffening members cannot be classified, but they are only used as parts of connection. As a result, for normal members, the user cannot control the length, but for stiffening members, you have full control over their length. And this is the property we will go and use in our connection here. We can see failures, okay, but the objective of this webinar is not to fix the failures, but to make this joint solvable. And I will go on and modify the joint from this working state. So I will go to my project items. I will create a copy. Let's rename this. Let's go back and see how are we going to define the lap splice version. We have to delete certain components from the original version. Let me also delete the ones that we're not going to use. We have to delete stub 1. We have to delete this base plate, and also the cuts, because they're irrelevant, as the stub 1 is deleted. So let's go on and modify the stub 1 with the stiffening member operation, which is here. I will define its cross section. I will then rotate it. And here you can see that I can define its length from both ends. So here I will send the value of 995 mils. And the next question is, okay, we defined the stiffening member, but we discussed previously that we should avoid defining eccentricities on member M3. So how are we going to move member M3? We have a solution for this. I will define a working plane. I will move the working plane in place. And then I will use this working plane to cut my member M3. I have to set that the cut will use a work plane. And if I look from the side, we can see that my member is cut where I wanted this to be. If I switch my view to transport to the wireframe, and select load case, you can see that the moment diagram extends up to the fictional node. Again, let me go back to my solid view. So now I can start defining my splices. For the splices, I will use the splice operation. Let's zoom in and look from this side. First, I will define the geometry of this splice, which is 15 mils thick. I will extend the splice on both members. And before I proceed with the modeling of the bolts, I will relate my splice to the stub. The stub is now the stiffening member as M1. The side effect of this setting is that the bolt grid is symmetrical. So I'm defining bolts at the top side, and the software creates a symmetric bolt grid at the bottom. Let's proceed with the definition. I have defined the column position. Now I will define my rows. The first splice plate is in place, and I just have to copy it and change the webs. I will also switch to the transparent view to be able to follow the replication process. And there it is. I will switch back to my solid view, and I will then create a new operation, which will be a cut operation, so that I can weld my stiffening member to my base plate. Now, remember that we were discussing that stiffening members can be manipulated on both ends. So now that I see that my stiffening member disappears, I just have to define which part will be cut off. And now that I have changed this part, this is welded on the base plate. And then I will also weld stub 2 on the newly created stiffening member as M1 with a surface cutting method, and I will set the weld throat thicknesses. Last, I will create a rib. Now, the user wanted to have a rib here, a gusset here. The easiest way to achieve this is to use our rib operation. Let me switch my view to transparent again to locate the ribs. So the ribs are located there. I will change their position. Let me change the view to solid view. I will look from the side, and I will have to change its geometry. So there it is. And now we have the full connection, which we can calculate. In the meanwhile, I don't know if we have any questions. Theodore?
Yes, actually, we have answered almost all of them, but there is a question that I think it would be interesting for all of them to hear about. It says, in case of calculating the assembly of 4 bracing diagonals with a middle gusset plate, with which diagonal should be selected as the bearing member, or does not affect the results? The same question in case of calculating a beam-to-beam connection.
Okay, this is this depends actually. When we have 4 members converging, then the recommended way of modeling this is to apply loads that are in equilibrium. If loads are not in equilibrium, then this can become tricky. If loads are in equilibrium, meaning that their vector sum is 0 at the position of the node, it does not matter which member will be the supported one. Now, it's the same for a beam-to-beam connection. If the loads you apply are in equilibrium, then it doesn't matter which member is the supported one. Now, if loads are not in equilibrium, then this is a little bit trickier, and there is not, let's say, one solution that fits all.
Just something to add here. Specifically for this, it is really important that you use the beam links. I think the beam links can help you a lot, because the loads that are coming from another structural analysis software for the global structure are in equilibrium by definition. So this is the best way to ensure that the loads are correct, and you will not have any issues, as you mentioned, regarding which one is the bearing member. So as Kostis mentioned, it really doesn't matter if the loads are equilibrium, and the beam link ensure exactly that. I have another question. If the bolts were to be changed to through bolts, does this have to be a manual operation?
Yes, yes, because you have to define. I think that the question refers to splice plates. So if you need to use through bolts, these bolts need to pass through 4 plates. So yes, in this case, we would not use the splice operation, but we would use stiffening plates as doublers, and then bolt through all these plates and the plates of the cross and the plates of the section.
Okay.
Okay, so let's also check, see the solution. We can also see the deformed shape here. And actually this is okay, so do we have time to go through the results maybe?
Just a little bit, yeah, just 1-2 minutes maybe.
Okay, so the connection is solved. Here we can see the strain check. We have a full view of all plates in the structure, and by plates we also mean parts of cross sections. Now let's say that I want to identify the source of the failure. Here in the plates I have a list of all plates. I have a red mark to the failing one, and if I click on these ones, then I can see, for example, M4 is a member. So here we have an unwrapped version of the hollow section, and we can see the failures. We have the plates of the stubs with some red marks, which means that these are positions of failure. The deformed shape helps also to identify the weak parts of the connections, and we also have results for each bolt. So I can select a bolt from this table. Then the software at the bottom displays the bolted plate, the position of the bolt on the bolted plate, and if I deactivate the deformed shape, the software also displays with an orange outline the position of the plate on the model. So I know exactly where I can identify the position of this bolt. And of course, if I press this plus button here, I'm extending this bolt row, and I have all the code calculations. The same is valid for anchors. We also have the welds here. You can see that when I select the weld, I can see the position of this weld on the plate that this is welded to. It is also showed here. You can see an orange outline. We can see the stresses, and again we can see the code calculations with formulas. So I think that we have nailed the time.
Yes, there are a few questions. I'll try to answer them very quickly. Which is the difference in between the bearing element and the supported ones? So actually, since we're running a 3D analysis of a joint, we need to have at least one member which is supported. So there is no difference apart from that. So one element is the supported one, and the rest can be loaded. This is the only difference. And apart from that, there is nothing else. I'm not sure if I answered the question, if I understand the question, but I think that's That's the answer, probably.
Theodore, maybe I can try to answer this also. I would like to add something to your answer. Maybe the terminology is a little bit confusing, because when we say that a member is bearing, we mean that it resists to load. So actually, all parts of the connection resist load. But in IDEA-STATICA connection terminology, bearing, let me go to the design here and select on member. Even stiffening members are bearing. They're not directly loaded, but they're loaded indirectly. For example, this member here is a stiffening member. It is not directly loaded, but load is transferred from this member through the connecting elements. Okay. So in IDEA-STATICA, when we say set bearing, we mean that this is the member we choose to apply the support. So this is member M3. If I choose it to be the bearing member, then supports will be applied to this end instead of loads. And when we have a number of elements in our connection, then only one of them can be the bearing one.
Okay, I will just answer one last question because I think we're running out of time. Is there any provision in the future for the allowance of reinforcement in the concrete block to get better pull-out resistance? This actually has to do with the Eurocode. So at the moment, there is no support of reinforcement. We cannot take into account the reinforcement in the concrete block. I think that with the new Eurocode that is coming, this will be supported, so then we can have a solution in the software as well. Okay, I think we can conclude. So I will just take the presenter back. Okay, so I think you all see my screen. So after the webinar, you will receive a short survey. If you can please fill this out. This helps us a lot to adjust the webinars and make it as better as possible. The recording will be available tomorrow in on our website and on YouTube. And of course, any of you who hasn't used the software so far, feel free to download the trial version from our website. It's a 14 days trial version. Our next webinar is going to take place on October 23rd. This is another Connection Wednesday webinar. And this will focus on IDEA-STATICA member. This is our brand new application for the analysis and check of the stability of members. And this will give you some idea of how powerful this solution is when it comes to analyzing a member together with all the boundary conditions, with all the connections that are involved. So please register for this webinar as well if this is something that interests you. So to conclude, I'd like to thank all of you again for participating in our first Connection Wednesday for this season. And we certainly hope that you found this interesting, you learned something today, and we're looking forward to see you in our next webinars. Thanks. Bye-bye.
Bye.